What's up, guys? Welcome to my channel, Science Portal. Today, we're going to be speaking about one of the most prominent chemistry topics today, which is the applications of chromatography in the separation of organic substances. And of course, I wasn't alone in composing and compiling this research. I got some help from fellow classmates and researchers, which I have mentioned in the box on the left. Also, don't forget to give us a thumbs up if you like the video and leave a comment in the comment section asking any questions you might have, and I'll try to answer all of them as soon as possible. Also, hit that subscribe button if you're new to the channel and hit that notification bell to get alerts every time new content is posted. Without wasting any time, let's get to the video. Before diving deeper into the topic, you might be initially asking yourself, well, what is chromatography, or what is chromatography used for? Well, it's not as hard as the wording may sound, as chromatography can be easily defined as a laboratory technique used to separate mixtures using a stationary phase and a mobile phase in order to analyze, purify, identify, and quantify the mixture or components. During this process, we originally have a mixture of two or more substances, which we are then able to separate into its individual components using chromatographic methods. We later on use these separated components to gradually analyze, identify, purify, and quantify each component independently. As you might have guessed from the wording, the stationary phase does not move, and the compounds in the mixture are attracted to it and slowed down. And also, the stationary phase is either a solid or a liquid. The mobile phase, unlike the stationary phase, has movement, and the more soluble compounds in the mixture are carried faster as the mobile phase moves. The mobile phase can either be a liquid or a gas. Now, over the years, scientists and chemists have found more convenient and accurate ways to enhance the precision and efficiency of chemical procedures. But out of all possible ways of separating mixtures, why do we choose to use chromatography? Well, it's simple and self-explanatory. Chromatography requires low sample volumes, which simultaneously means there will be a smaller margin of error during the determination of components. Secondly, all the mixture components separated can be collected individually, which gives us the advantage of knowing and understanding all the properties coming from each part mixture. And lastly, it can work on a lot of different samples, such as food particles, pesticides, air and water samples, drugs, and tissue extracts. And of course, there's more, but here we're only going to mention three, which is the three most relevant according to our research. Now, like every other chemical method, these chromatographic procedures have their own set of downfalls. These include the fact that the instruments used for chromatography are quite expensive, which then means the equipment can only be operated by a trained person, and it must also be handled with care because of the sensitivity of the equipment. Secondly, errors may occur if samples are overloaded, and lastly, some methods used for chromatography require high power consumption, which has the greatest downfall of all. With the growing innovations comes more chromatographic methods for chemists, but here we are only going to discuss the two most used, which is column chromatography and paper chromatography. Now, if you have these two methods side by side, you will notice how they differ and the different apparatus used for each. On the left, we have our column chromatography, which is a method used to isolate a single chemical compound from a mixture. On your right is your paper chromatography, which is a technique for separating dissolved chemical substances by taking advantage of the different rates of migration across a sheet of paper. Okay, please watch the following short clips on column chromatography and paper chromatography, which I was able to make and conduct during our lab experiments. Now, this video right here was for the determination of dichromate and permanganate in a sample by means of chromatography. The yellow part is the dichromate and the purple part is the permanganate, which is being collected into the beaker at the bottom for determination. This whole mixture started out as a homogeneous mixture, which was then separated into its individual components, then collected to be determined. Also, please watch the following video on paper chromatography. This video right here illustrates what happens during paper chromatography. As you can see that as the solvent front advances upwards, the spots run up. Here, the mobile phase is a solution at the base, which here is ammonium, also known as NH3, butanol, and water. And the stationary phase is the chromatography paper. Almost impossible to conduct an experiment free of factors that will interfere with the process of that particular experiment. Now, chromatography is one of those experiments, and factors affecting it can include eddy diffusion, which is affected by the nature of material packed in the column. This includes particle size and particle shape. Secondly, we have longitudinal diffusion, which is caused by the concentration differences in the mobile phase. Now, longitudinal diffusion is where the solid moves from the concentrated area in a backwards and forwards direction. And lastly, we have mass transfer, where there is no equilibrium between the mobile phase and the stationary phase. This is due to that after some time, a reverse process occurs as the analytes move from the stationary phase to the mobile phase, thus resulting in a continuous mass transfer happening between the flowing mobile phase and the stationary phase during the course of separation. Well, there are many ways in which we can minimize the effect of these factors so as to improve the efficiency of chromatography. These include decreasing particle size, since changing to particles that are half as big while keeping the column length the same will double the performance but increase the required pressure by a factor of 4. Secondly, we can ensure sample stability, as we might know that many issues including missing peaks or poor repeatability have been seen during chromatography and are caused by reactive sample pathway transfer. And lastly, we can improve detection limits by an order of magnitude, since detection limits of sampling and analytical methods are being challenged by environmental regulations in such a way that all methods that produce consistent ppm level results are no longer applicable nowadays in ppb and ppt regulatory environments. Parts per billion and parts per trillion are assuring to give precise sample analysis. There is obviously a number of examples or real-life examples for the use or applications of chromatography, but here we are only just going to mention 5. Well, firstly, chromatography can actually be used in hospitals where it is used to detect blood or alcohol levels in patients' bloodstream. Law enforcement uses it to compare a sample found at a crime scene to samples found from suspects. Manufacturing plants use it to purify a chemical needed to make a product. Pharmaceutical companies use it to determine the amount of each chemical found in a new product. And lastly, environmental agencies use it to determine the level of pollutants in the water supply. Now, guys, that's it for our video today. I hope you enjoyed it, but most importantly, I hope you found it very useful and informative. Thank you for viewing and keep that notification bell on for more content. Also, share the video as you may never know who is struggling with the topic we just touched up on.